Buenos días. Va a comenzar ya el workshop propiamente dicho con la lección inaugural que va a impartir el profesor Shtub. Pero antes de que pase a hacer su exposición, me gustaría hacer una breve introducción a su personalidad. Bueno, antes de nada, quiero dar las gracias porque se me haya brindado la oportunidad de presentar a un ingeniero industrial en una escuela de ingeniería industrial y por parte de un ingeniero industrial. Esto siempre es de agradecer y, sobre todo, ver la confirmación de lo que a lo largo de nuestra docencia, tanto en esta escuela como en las otras escuelas de ingeniería en la Universidad de Valladolid, los que impartimos materias relacionadas con la empresa, a ingenieros de distintas especialidades, insistimos de forma, yo diría que a veces hasta tal vez excesiva, en la importancia de la vertiente directiva de los ingenieros y de la importancia del factor humano. El factor humano, como acaba de mencionar el director de Michelin, es uno de los factores críticos y el que más dolor de estómago suele generar a los directivos en las empresas. Los problemas técnicos, pues más o menos se pueden resolver. Los problemas humanos son problemas terribles, de resolución enormemente costosa, etc. Bien, la ponencia de hoy tiene mucho que ver con esto, porque tiene que ver con cómo entrenar a ingenieros y cómo entrenar a ingenieros en dirección de proyectos, y sobre todo cómo entrenar a ingenieros para que aprendan y luego no olviden lo que han aprendido, porque parece ser que la curva de olvido del aprendizaje es una curva dramática, sigue la ley potencial, rápidamente uno olvida pues, prácticamente todo a las pocas horas o pocos días lo que ha aprendido. Entonces el mantener un grado de conciencia de lo que se ha aprendido parece ser que no es tan sencillo ni tan trivial. Eso es algo en lo que el profesor Shtub es un especialista y por eso es enormemente interesante y estimulante escuchar lo que nos va a decir. En cuanto a su currículum, ahora voy a hacer la presentación en inglés para que, a petición de los organizadores, para que, en fin, hacerle el honor al conferenciante y al resto de colegas que puedan estar presentes. The Professor Avraham Shtub holds the Stephen and Sharon Seiden Chair in Project Management. Is a senior member of the Institute of Industrial Engineering in the USA. He has been recipient of the Institute of Industrial Engineering 1995 Book of the Year Award for the book entitled Project Management, Engineering, Technology and Implementation. He is also recipient of the Production Operations Management Society Wick Skinner Teaching Innovation Achievement Award for another book, which is entitled Enterprise Resource Planning, The Dynamics of Operations Management. Also, he has a couple of books in Hebrew, Project Management and From Operations Management to Plant Management, Introduction to MRP, ERP Systems. Hago un inciso, es una pena que estén en hebreo. Estos dos libros que acabo de mencionar son los libros estándar en las escuelas de ingeniería en Israel y de difusión masiva en ese país. Lo que pasa es que están en hebreo. Ahora le diré si existe alguna posibilidad de que los vayan pasando al inglés. I'm saying that your two books, Project Management and From Operations Management to Plant Management, are in Hebrew. It's a pity, because the Hebrew is not a very extended language here in Spain yet. Also, the Professor Shtub is a department editor of the Industrial Engineering Transactions and a member of several editorial boards of international journals, has been faculty member in the Tel Aviv University, and actually is a member of the Technion Israel Institute of Technology, which is the most important institute of technology in Israel. And finally, he has been consultant in many industries all over the world, in Europe, Far East, North America, South America, Australia, and visiting professor in many universities. His research focus is oriented to three main issues. The first is design and management of manufacturing systems. The second is project management. And the third is learning and forgetting, which is something very interesting to see, and I think that this has to see with his presentation. And his actual current research projects are development of new teaching tools for industrial engineering operations management, design of human-computer interfaces, and design of project management and control systems. Después de esta introducción necesariamente breve, Le cedo la palabra al profesor Shtub para que nos haga su presentación de la conferencia titulada New Tools for Teaching and Training in Project Management. Profesor Shtub.
Thank you. Good morning. Can you hear me? Thank you for the opportunity to visit here, your beautiful country, and to speak to you. My presentation is about training in project management, both for students at universities and in industry. And I will start with a general overview of training and the new approach of serious gaming to training. And then I'll talk about some research issues in the area of training and simulators. And finally, I will present a simulator that we developed at the Technion. Now, I know that there is simultaneous translation here, so if I'm going too fast, just raise your hand and let me know, and I will try to slow down. Thank you. How do we teach? Well, I'm looking at this class, and this is pretty much what I see. People are sitting together, somebody is speaking, and they're trying to listen to him sometimes. And the main impact of this way of teaching on students is that they are getting bored. And we're stuck. And about 10 years ago, there was a survey in the United States looking at why students dropped high school. And it turned out that boring was the #1 word that described the school experience of those students in the United States. Is there any change? Not really. In 2006, there was another survey, and about 50% of the students who left high school did so because they were bored. And when I asked my students about teaching at the university, teaching at the Technion, and I asked my son who is here, they always tell me that it's very difficult to sit all day in a lecture hall like this one, listening to professors, and after 2, 3, 4 hours, it's just impossible. Is there another way to teach? Yes, there is another way. What you see here is a game. It's called the Flight Simulator. And it's a commercial game which you can purchase, install on your computer, and play with it. The interesting part is that in many airliners and even armies, flight simulators are used to train pilots. Why do they use simulators? Why not lecturing? There are several answers to that, and I want to go to an old research and talk about it later, but we'll start with an initiative, a relatively new initiative, 6 years old, in the United States, called Serious Games Initiative. And a lot of money was available in the United States for the last 6 or 7 years to develop games for teaching at the university and the high school level. There is a community nowadays called the Serious Game Community. They have conferences every year, and from year to year you see more and more applications of this approach. The approach that says no more lectures, no more lecture halls. We want to teach the new students, both at the high school level, at the university level, by playing games, by using simulators. And there are many, many examples. I will talk today about only 2 of them, which are simulators for engineering and simulators for management. Project management is an area somewhere between engineering and management. And the simulator that I'll show you toward the end of my lecture, it's a simulator that was developed at the Technion, my university, and is currently used by several universities in Israel and in the United States. And it's on the borderline between engineering, the engineering aspect of project management, and the management aspect of it. But as you can see, in serious gaming, there are many, many examples in different areas. Areas like astronomy, archaeology, architecture, atmospheric sciences, biology, chemistry, computation, fluid dynamics. and so on and so forth. So there is a trend, and it's growing fast. There is a lot of interest, and maybe, I don't know, it's the right way to go. And I hope that after the lecture, you'll have a better feeling for it. As early as 1987, some 20 years ago, papers started to show, talking about the use of simulation and the use of games for teaching. And the focus was on why. Why do we want to use simulators for training and for teaching? Well, this is an old paper, a 20 years old paper, that comes up with very interesting observations. First of all, when you are using simulators, you are emphasizing questioning and not answering. The students are facing a question. And when my kids were young, I remember my son playing with SimCity. SimCity is a project management tool. The project is to develop a new city. And he spent hours and hours. I had to fight with him to stop playing. Why? Because there were always new questions coming up, new problems to solve. It was interesting. He liked it. It was fun. And that's the whole idea. Make learning fun. Can we do it? Maybe. I don't know. Another point is that while doing the games, while playing, we are actually making decisions. And we are making those decisions while looking at some assumptions and implications of these assumptions. We don't take anything for granted. You make some assumptions, you make decisions based on these assumptions, and then you see what the results are. And based on the results, some critical thinking can help you decide whether the decisions and therefore the assumptions were right or wrong. The nature of the problem you are dealing with is exposed because you are getting to all sorts of details. And the nice thing about gaming is that you can start with a very, very simple game at the introductory level. And the more you play, the more difficult it is. So actually, you can design games that encourage the student to look at more and more difficult problems, but they do it gradually. So he's learning while solving those problems. An environment is created, an environment of discovery. Every time you play, you discover new aspects. You learn by discovery. And this is the best way of learning because it has to do with the natural curiosity of the students. Skills in communications and role-taking are also developed in some games. These are games where groups are playing. Not a single person, but several people playing the same game together. And for example, nowadays you can use the pilot simulator in a group where people are playing dogfights in airplanes. I fly my plane, you fly your plane, and the two computers are connected. So a group learning experience is now developed. And therefore communication between people, the ability to lead, the ability to solve problems together, all of this can be done using simulation games. If you look at kids playing games, you see a lot of motivation. Usually you don't tell them, go to your computer and play some games. What you have to tell them is to stop playing and go outside and play with their friends. Why is there such motivation? Because there is fun. Because there is a learning process that involved our intuitive way of learning. And then there is much more attention. People remember more, and that's an important point. How much do we remember from a lecture? How much you will remember from my lecture next week, next month? Well, there is a decay, and it's fast. Within a month, you'll forget about 50% of what I'm saying. Within a year, I don't know if you remember that I was here. When you are doing games, you remember much more because it's learning by doing. You actually do whatever you learn. And therefore, retention is much better. Understanding is deeper. The process of learning is not oriented to the end results. You enjoy the process itself. You are playing, therefore you are enjoying it. It's not just to take the test at the end of the semester. And we have many complaints at the Technion. Students are complaining, you are teaching us how to take tests. You are not teaching as engineering. That's not the way it is done in playing games. When you are playing a game, you are in the process. You're learning from the process itself. It's not just the end result, which by itself may be important. In the last 5 years, some books were written on the theory of learning using games. It's a new theory. There is a lot that we don't know. There is a lot more to learn. And as I said, the serious gaming community is publishing papers, publishing books, and of course, meeting in conferences to share new knowledge, new information, and to look at the new problems that are coming up in this fascinating area. I want to show you a game, a computer game that was developed at the Technion. It was developed originally as a contract with the Israeli electric company. About 15 years ago, maybe a little more, they started to build gas turbine power plant. The first one was built in Israel about 17 years ago, and then they decided to go for some more. And the idea was to develop a simulation where teams doing gas turbine projects will learn from the first one that was already completed. So we simulated a real project. And then the people from the Israeli electric company came and managed that project on the computer in a classroom, and the trainers were the people who already participated in the original project. And it was a success, to such a degree that I decided to develop a simulator that will be used in my class. And if we look at the area of serious gaming, we see that there are three major issues. One is the theory of learning. Second one is the design of your game or the simulator. And the third one is the content. And in our initial effort to develop a simulation, we were looking mainly at the learning process, the learning curve, trying to develop a simple simulation and trying to focus on both the management aspect and the engineering aspect of project management. There are several principles that we adopted in developing the simulator. We called it, the original one was called PMT, Project Management Trainer. And in the last 2 years, we developed a new one, which is called PTB, is Project Team Builder. The main difference is that the new simulator is for team learning. Several people can manage several projects simultaneously in a matrix-like organization. So they share resources and they share information, and it's exactly like the pilot training, where you start with a single pilot and then you have several people flying several airplanes on the simulator simultaneously. So first of all, it's a simulation approach. Actually, we are trying to simulate projects, but in the new simulator, we have two parts. One is the simulator engine, which is a standalone piece of software. The other one is a library of scenarios, of case studies. So if you teach construction, you can take a scenario of building a new bridge or building a new house. If you teach computer sciences, you can take a scenario of developing new software. Any scenario can be used with the simulation engine. And basically, it's a case study approach. You can take your old project, one that was finished, and you have a lot of information on it, like we did with the Israeli electrical company, and then simulate it as a case study with your class. However, unlike the case studies that are usually used in universities, like Harvard case studies, if you are using them, it's not a piece of paper with a story. It's dynamic. Everything is changing throughout the simulation. Also, within the simulation, there is a model base. Several models that are typically used in project management. For example, we have a Gantt chart, we have a critical path analysis, we have resource graphs and histograms, we have cash flow management tools. All of these are available to the user. All of these models are very simple, easy to use, and available throughout the simulation. There is a database approach in the simulation. We keep all the history of the simulation. We call it history mechanism. And after a simulation run, the student can go back in time and see what happened. Furthermore, if he is doing it with a teacher, he can go with his teacher back in time, see what decisions he made, and analyze those decisions to decide and to learn from the past. It's an integrated approach because you can run more than one project at a time by more than one person. So we called it Project Team Builder, as a team of students or team of people in industry can run several projects simultaneously, sharing resources and sharing information. I was working for 2 years now with a professor from Drexel University, a professor of psychology and computer sciences. His name is Tom Hewitt. He is in Drexel in Philadelphia. And we try to develop a friendly graphic user interface, which is his expertise, not mine. The target was to develop a user interface such that there is no need to teach a student how to use the simulator. It will be completely intuitive. You take the simulator, you start running right away. We didn't get there. We still need to spend about 30 minutes teaching a new student how to use the simulator. It's not completely intuitive, but we would love to develop such a user interface so that anybody can log into the simulator and start running projects without any instructions. It is also integrated with commercial software. When we use the simulator in industry, it is integrated typically with Microsoft Project. So the student can see the simulation, see the project he has to manage, transfer all the data automatically to Microsoft Project, and then do the analysis on Microsoft Project, going back and manage the project. There is a library of scenarios, and basically we developed a scenario generator. It's a software tool by which the teacher can decide what he wants to teach. Do I want to teach construction? Do I want to teach software development? Or any other area in project management? And then I develop my own scenario, and I can focus on the specific points I want to teach. For example, in some scenarios, the focus is on resources. So there is a limit of resources, and the students must schedule the project under resource constraints. And tomorrow, Professor Willy Erlin will be here and will tell you a lot about scheduling under resource constraints, which is his expertise. In other scenarios, we are dealing with cash flow analysis. The amount of cash is limited. There are some payments along the project, milestones for payments, and the student must learn how to schedule those payments early on so he will have enough cash to finish the project. So each scenario is on a specific domain and dealing with specific issues. I'll show you some of the screens of the simulator just very briefly. We don't have much time, and then we'll go to some research questions. So when the student gets into the simulation, he's first getting information about the scenario, about the project he needs to manage. Starting with some information about each task. This is the task planning screen. What you see here is the task number. This is task number 4, the task name, system requirements. Whether there is any income associated with the task, when you finish this task, you get $50,000. This is very important in cash flow management. And there, how many ways are there to perform the task? In here, there are 2 different ways to perform the task. We call them mode 1 and mode 2. For example, suppose you can do it in-house or use a subcontractor to do it. Each mode has a distribution of time, optimistic, most likely, and pessimistic. This is the PERT model, which is used in project management. And for example, if you do it in mode 1, the optimistic time is 8. However, if you decide to do it in mode 2, the optimistic time is 10. So mode 2 takes more time. Then we have the cost issue. If you decide to do it in mode 1, there is a fixed cost of $3,000, and on top of that, you have to pay for the resources. In this example, there are 4 different resources. 3 times $3,000 is $6,000. 4 times $3,000 is $8,000. 4 times $8,000 is $12,000. 4 times $12,000 is $16,000. 4 times $16,000 is $18,000. 4 times $18,000 is $19,000. 4 times $19,000 is $20,000. 4 times $20,000 is $30,000. 4 times $30,000 is $40,000. 4 times $40,000 is $50,000. 4 times $50,000 is $60,000. 4 times $60,000 is $70,000. 4 times $70,000 is $80,000. 4 times $80,000 is $90,000. 4 times $90,000 is $100,000. 4 times $100,000 is $200,000. 4 times $200,000 is $300,000. 4 times $300,000 is $400,000. 4 times $400,000 is $500,000 a software engineer, a system engineer, and so on and so forth. And each mode is defined by the duration, which is stochastic, the fixed cost, and the number of units you need of each resource type. So for example, in mode 1, you need 3 systems engineers. In mode 2, you need only 1. Maybe because the work or part of it is done by a subcontractor. So the student, when he starts, has to decide how to perform each task, in what mode. It is done here. He is selecting the planning mode, and then he's selecting which mode he wants to use. And finally, he has to decide on the starting time of the activity. By going through all the activities, the student can actually plan the project. And at the end, he will get a project plan. Then there are precedence relations among the tasks, as in any project. And these can be seen either by a table, like here. We have 16 tasks, and task number 2, system architecture, is preceded by 2 tasks, 0 and 1. If the student tries to schedule task 2 before 0 and 1 are finished, the computer will come and say, you can't do that. So he learns that there are precedence constraints. Then the resources are well defined. These are the 4 resources we saw earlier, but also each resource has a cost. And again, when the instructor decides on the scenario, he has to decide on the number of resource units available per day, the cost per unit each day the resource is working, and also there might be a cost if the resource is idle. In advanced scenarios, we let the student hire and fire people. So if he thinks that 6 software engineers is not enough, for a cost, he can hire more software engineers. If 6 is more than enough, he can fire some. Again, there is some cost involved. And finally, the cost is very important because most of the projects are done for profit. So we have all the cost information available. Very important, in many scenarios, there is a bonus per day. The project has a due date of 40 days. However, if you finish in 39, you get a bonus of $5,000. So there is a trade-off between the cost of resources and the bonus. You can add resources, finish earlier, you get a bonus. Because the problem is stochastic, there is a clear need to manage risks in this scenario. So you have to take into account the probability that the worker will not come to work, which is built into the scenario. You have to take into account the duration of the activities, which is stochastic. So the problem may be very, very difficult to solve, but as I said earlier, we always try to start with very simple scenarios. And one thing that is very interesting, when I'm teaching a regular class, like lecturing, most of the time the students are complaining that the tests are too difficult, homework are too difficult. When I ask them to do it with the simulator, they typically complain that the scenarios are too easy. They want more difficult scenarios. And maybe it's an indication that the early paper we saw from 1987 is correct. The user has a goal, a specific target. He must finish his project on time at minimum cost. Of course, I tell my students that there is no exam in the course, and the grade is based on the results. So they are highly motivated. Furthermore, I can use the same simulator with the same random generator for all the students, so they compete with each other. And they're simply running the same simulations. And therefore, I can rank them on a scale with the best result first, the last result last, which makes a lot of interest within the student community. There is a network view, and what you see here is the main screen of the simulation. Each of these is a task. The number is the task number we saw earlier, and the numbers can be in one of 4 colors. A green number means that the task is not planned yet. We did not decide on the mode, we did not decide on the starting date. A yellow color says that we already planned the task. We have a mode, we have a starting date. When the task is in red, it means that it is in process. We started working on it, not finished yet. When it is in magenta, the task is finished. The lines represent the precedence relations among the tasks. And here is the main control of the simulator. This is the time in the simulation. We didn't start yet, so it's time 0. This is how much money we have. Right now we have $12,000 available to us when we start. This is how fast we want to run the simulation. Do we want to run 3 days at a time, 1 day at a time? And the student makes his choice, and in some scenarios, I give them limited time to run the scenario, and this is the real time. So I say, you have 10 minutes to run the scenario. And if you pass the 10 minutes, you failed. So it's decision-making under time pressure. As I said, the basic step, the first step is to plan each task, to decide on the mode and to decide on the starting time of the task. Once the tasks are planned, you can draw a Gantt chart, and this is a scenario with 2 projects. This is the first one and this is the second one. The red tasks are tasks that already performed. This is time 1. I don't know if you can see the dashed line here. This is the day where we are. Now, the actual duration of each task is not necessarily according to the original plan because of uncertainty. The availability of resources is not necessarily according to the plan because of uncertainty. In parentheses, actually, the first number you see is the task number, and in parentheses is the resources required. In this simple scenario, there is only one type of resource, called it a worker, and for example, task number 3 requires 1 worker at a time. So the student learned that he can sum up the number of resources required, and for example, in day 1, he needs 12 plus 3 plus 1 plus, 2 plus 3 plus 1 plus 2 plus 3 plus 1. So this is the total number of resources required, and he can compare it to the number available. So there is a better way to do it. We call it the resource graph, which is automatic, and the student can see his plan versus the availability of resources. In here, in this scenario, there are 2 workers available, and on days 3, 4, and 5, he needs 3. So he needs 4 workers. Therefore, the solution, his plan, is not feasible. And he must go back to the planning board and change either the mode or the starting time of activities. Another way is to hire more resources. But when he gets to day number 3, the computer will not let him run anymore. He will not be able to run the simulation because his plan is not feasible. He can double-click on each of the bars, and he will see which activities require this resource on that specific date. Once you start running the simulation, you have to control the situation. Basically, monitor the actual performances and compare them to the plan. Again, there are models for doing that, and before getting into all these models, we have to consider the one last aspect, which is cost. What you see here is 3 views of cost. This is the cumulative cash flow. This is the daily cash flow, and this is the detailed cash flow or a budget of the project. And once you plan the project, you can see his budget. All the numbers are here. And actually, you get an estimate for the profit that you will make at the end of the project. However, because of uncertainty, the actual profit may not be the same, and therefore there is a need to monitor and control this project. There are several models used for monitoring and control. In here, we get a general picture. What is the direct cost so far? What is the indirect cost? How much penalty we are going to pay? What is the total cost? the income from tasks, the bonus if any, and the total income. In here, we have two detailed tables. In the first one, the control is based on a daily analysis. How much money we plan to spend each day, the first day, what was the actual cost, and so on and so forth. The second table is at the task level. Here is the first task. This is how long we thought that it will take. This is how long it really took. How much we thought that it will cost. What was the actual cost. And therefore, we can see easily all the deviations between the actual and the plan. Now, when I'm teaching this in industry using the simulator, they are not using my tables. They transfer everything to Microsoft Project, which is very easy, and then do all the analysis on Microsoft Project because they are used to Microsoft Project. And many times, we teach Microsoft Project using the simulation. If you have any question, I'll be happy to answer. If not, we'll go to some research. Okay. There is a lot of research performed on simulation and the use of simulation for training. Last year, I was asked with two friends of mine, Tom Hewitt from Drexel University and Abraham Perush from Carleton University in Canada, to edit a special issue of the International Journal of Engineering Education, an issue that is devoted to simulators and engineering in education. Turned out that there were like 50 papers submitted to the special issue, of which 15 were accepted and now are under final revision. And to my surprise, of the 15 papers, 4 were authors by people from Spain. So this is the first one. I don't know if you know these people. I don't know them. That's a group from Universitat Politécnica de Madrid. This is the second paper, University of Navarra. Third one, University Politécnica de Madrid. And the last one, from Zaragoza, Spain. So out of 15 papers, about 25%, a little more, are from people from your country. So there is a community in this country dealing with serious gaming, doing work on simulators. And of course, this is, I believe, just the tip of the iceberg. There are many more, and they simply did not submit papers to the special issue. What are the issues that people are dealing with? Most importantly is the design of new simulators. People are trying to develop simulators for their needs, for their classroom. People in mechanical engineering are dealing with refrigerator cycle. People in software engineering are dealing with the development of new software, and so on and so forth. But people are starting to see the benefit in using simulators in training. Then, as I said, a major issue is the human-machine interaction. We don't want to teach simulation. We don't want to spend time teaching students how to use the simulation. So we want to develop a human-machine interface that is very intuitive, so that a new student can get into the simulation and start working right away. We don't want any setup cost. We are not there yet. For example, in the simulator we developed, there is still a need for about 30 minutes learning of the simulator itself. Simply learning the screens that I showed you earlier. History recording is becoming a very important issue. It turned out that if you let the user, the student, look at his past decisions, he is learning much better. We can take it further. If you have a group of people using the simulator, and then they do a formal debriefing analysis, looking at what they have done, and asking questions why we did it. Could we do any better? Could we get other results? The learning is much faster and much better. Another point is visualization. How do you present the data to the student? For example, you saw the flight simulator. In the flight simulator, visualization is very much like the cockpit, what the pilots see in the airplane. However, we have no cockpit in project management. So what should the student see? Should he see a construction site? Should he see a screen like Microsoft Project screen? What is the best visualization so that he will get most of the data easily and he will retain the information, he will not forget? We don't know yet, but there is a lot of research in this area. Another point is how to develop courses based on simulation. Like I'm teaching a project management course which is completely based on the simulation. It took a lot of time to develop it because there is no theory yet. If you search for a book telling you how to develop a project management course based on simulation, you will not find such a book, or at least I didn't find. So there is a need to develop some guidelines, some theory. What is the best course? The new trend is web-based simulators. So you don't have to get a CD or a disc from me. You go to the web, you log in, you start playing. The problem is that most simulators are several thousand lines of code. So they are heavy software. And when you do it through the web, many times it's getting slower. And the students like fast reaction. They don't want to wait. So right now there is a trade-off between the speed and the accessibility. I believe that in the future, most simulators will be available on the web because our communication is getting faster, the bandwidth is getting cheaper, and accessibility will be the driving force. So simulators will be, you go to the web, you log in, and you can run the simulation. No need to install it on your computer. Another trend is group simulators, where several people are running a simulation together. The benefits are clear. People learn to communicate. People learn to lead. People learn to take roles. The technology is still in its infancy. For example, if you want several people to manage a project or several projects, you have to wait for everybody to make decisions in order to advance time. Should it be synchronous or non-synchronous? So there are very different problems to look at. It depends on the simulation, it depends on the technology you are using, and of course it depends on the way you design your course. And most important probably is, are simulation really more efficient and more effective in teaching? Can we measure it? Can we prove that by using simulation we learn faster, we learn better, we retain the knowledge, and we can transfer what we learn in the simulation to the real world? All of these are questions that research has to deal with. There is a new area of research, and here some psychologists are involved. It has to do with meta-skills, meta-knowledge. The idea is that can we learn what happens in our brain when we learn? Can we control it? Can we develop a simulation where a person will say, I want to learn this, therefore I'll do this? There is some theory developed already. I don't know of any simulator that is really using meta-skills and meta-knowledge in teaching. And finally, many of the papers were simply case studies. Somebody reporting a simulator he developed and used in class and developed and presenting some results of these simulators. If I want to summarize all of this research, we can say that there are two major issues. I call them efficiency and effectiveness. Efficiency, can we reduce the time it takes to reach a specified level of performance? Can we teach faster? Effectiveness, can we use simulator to teach better so students will understand better? They be better doctors, better engineers, better pilots because they were trained using simulators. I think these are the main issues. And along these lines, I was trying to do some research with my students. And our research focused on 3 points. One is individual learning. a single student using a simulator, our simulator. And at the individual level, we were trying to look at the learning curve. How fast the student is learning when we use the simulator in different ways. And one thing we wanted to look at is the history mechanism. What happens when a student has access to his past decisions? Can he learn faster? Is it a better learning process? A second avenue of research is learning, forgetting, relearning. As I said, there is a decay. People forget. After a month, you will remember only part of what I'm saying here today. Question, can we use simulators to fight forgetting? And I can tell you that it is done already. Pilots are trained on a regular basis with simulators so that they will not forget anything. But we are trying to measure how much forgetting we can fight with history mechanism and with simulators. And finally, the last avenue of research has to do with group learning and the impact of history mechanism on the group learning and debriefing done by the group. So, we start with the first hypothesis, which is if you use history mechanism, if you make history available to the student, then the learning is faster. And we looked at several types of history mechanism. One is the undo. You simply go back in time, like undo in Word or in Excel. You go back to the previous stage. Another one is just save. You save the situation, and then you can look at it, but you cannot restart from that point. You can only analyze it. Then we implemented a debriefing procedure, which was simply a discussion by the group in which they were asked to discuss what kind of decisions they made, what actions they took, and what were the results. And because everything was recorded in history, they could go back, look at all the history, discuss it, and come up with new knowledge that they could apply in the next simulation run or on the next scenario. So this is the first paper we published. It was in 2006, and it was published in the Journal of Engineering Education. Had to do with performance and transfer at the individual level, single user. And we took students in my class, 98 students in the 4th year of industrial engineering, and they had no practical experience with project management. Undergraduate students, no experience. And then we were asking them to use the simulator. And we divided them into groups. The first division was people who had manual history mechanism as opposed to those who had automatic mechanism. In a manual mode, you have to decide what you want to store. I want to store this point of time. And you have a limited number of time periods you can store. So here's a constraint. Suppose you can store 6 points of time. Now you have to decide what you want to store, which makes you think about what is important in the learning process. What do I want to be able to go back and investigate? In automatic history, everything is stored and then made available to you. Then we had a control group that couldn't look at the history at all. Within these two groups, one had the ability to undo, going back in time and rerunning the simulation. And the other one couldn't undo, which means they could only look at the history but not rerun the simulation from that point. Then, let me get back here. There were two phases. First, they ran a single project simple scenario. Then they ran, after 3 times of this one, the 4th scenario was a multiple project, more difficult scenario. And here you see some information about the simple scenario. Here it is. 16 activities, very simple. And this is the set of resources, 4 different resources that they used in the simple scenario. Then they had multiple project scenario with 2 projects, 24 activities. These are the 2 projects. You see project 1 and project 2, and these are the activities up to here of project 1. These are the activities of project 2, the activity number and the precedence relations. And here are the results, and it's amazing. Turned out that the people who did best were those people who used manual history. They had to think what they want to record, which means if you make people during the learning process think about what they have learned and what they want to recall, you make the learning process better. At least judging by the end result, which is profit. And it's true for both the people who used undo and the people who didn't use undo. Manual history is better. And this is in terms of how long it took to run the simulation. And again, you see similar results. Here we see a picture of the results. Basically, it's the same information, but there are some interactions. You see that these lines cross each other. That's the first study we did. Here is the second one, and a little bit behind time. Can we go further? Can I continue? It's okay? Okay. This is the second study. It was published this year in April in Computers and Education, and it has to do with learning and forgetting and relearning. Here the question was, if you have a break in the learning process, how much people forget during the break? And again, we had groups using different kind of history mechanism. There was a 2-week break and a 4-week break. And there were 2 phases, a basic learning, where they did the simulation several times consecutively. And then there was forgetting and relearning. There was a break, and they get back to the same scenario. And finally, there was transfer, where the student had to run a different scenario. So what we saw is a very similar result. When you look at the history mechanism, the best results are with manual history, this one. And when you look at the break, 2 weeks and 4 weeks, with a shorter break, manual history is much, much more significantly better than the automatic history. This is the duration and a completely different picture. With the duration, no history take the longest, manual take the shortest, and here you see that again they converge after 4 weeks. What you see here is the mean profit on run 6 and 7. 7 is a transfer to another scenario. Run 6 is after forgetting. And again, you see that the manual history is always better. There are more results here. I don't want to get into all the details. But the one thing I want you to remember, make your student think about what they want to record. Give them a constraint. They can't keep all the history. They can keep part of it. And then they will get involved in the learning process and will get better results faster and forget less. That's the main issue here. That's the last piece of research. We are still doing it. It has to do with team learning. Here, several students had to manage several projects in a matrix-like organization. They had to share resources. Some students were experienced, some were not. Some were undergraduates, 60 graduate students with at least 3 years experience of project management, 72 undergraduate with no experience. And these are the groups in the study. Some had history, some had not. Some had structured debriefing. We told them how to analyze the results at the end of each run. Some had no structured debriefing. The random generators for the stochastic processes were all the same, so we knew that the students are running the same scenario under the same conditions. And this is the structure of the study. 2 phases. A basic team scenario, phase 1, running it 4 times, so they are on a learning curve. And then an advanced scenario, a more difficult scenario, which is phase 2. And of course, you can see that some of the groups were graduate students, others were undergraduate. Within each class, there were some with history, some without history, and then within each class again, some were with debriefing and some without. And we looked at the results, and we saw just very briefly that for the experienced students, the combination of history mechanism and debriefing made a difference. They got much better results, the profit was much, much higher, and they did it much faster. So history mechanism and debriefing seems to be the way to go when you are teaching teams of project managers. And the next step is to introduce the right visualization into this and see how you can present history the best way to enhance learning and to reduce forgetting. To summarize, we are only at the starting point. There is a lot more to do with simulation. And I believe that almost every engineering area can be taught using simulators. And within time, such simulators will be developed and will become popular. I just hope that I will get to see the results. And finally, I think that there will be a trend in industry too to adopt simulators. And instead of teaching people on the job, which is very expensive because errors are expensive, we will see in industry training using simulations and games where people can make mistakes in a controlled environment, the cost of mistakes is low, and they can learn from their mistakes. Thank you. If you have any questions, please.
Is there any way of introducing the human factor in this simulation?
Yes. There are other project management simulators that are focusing on the human factor. Actually, you can hire different people. You see the CV of each of them. You see some information about their behavior. And once you hire that person, he will behave in a random way according to his CV and the data you got. Yes, it's available. Other questions? Thank you very much. Yes?
And well, basically, I think that some of the things that you've been saying, and probably I would agree with them even before seeing the studies, you know that probably this is a better way, this is more fun. But one thing that I have, a question that I always have with this is whether the studies take into account the time that the students need to get the concepts. I mean, I am sure that they get much stronger hold of the concepts. But have you made any study about the difference in the time that they require to get them? I mean, probably with a more classical approach, the time that you dedicate for them to get some ideas is shorter than what they require using a simulator. Is that right, or?
I don't know if it's right. I can tell you about my experiments, my research. What we did, we took students that took my course. They already knew the concepts because I taught them in a regular class. And then they used the simulation. I never tried, and it's a very good idea, to take somebody who has no idea what project management is all about and ask him to use the simulation. I never did it, so I don't know what the answer is.
Thank you very much.
Yes, please.
This is in relation to the interface. You mentioned that you were trying to make some research on what kind of interfaces for this type of teaching. Have you explored something already, or is just an idea for the future?
Yes. We developed a new interface. It's not implemented yet. And the idea was the idea of Professor Wick, not mine. The interface is based on the traffic light. Everything is in 3 colors, yellow, green, and red. And when you see red, you know that you need to pay attention. So all the screens are just yellow, green, and red. You see the resources in the same colors, time, money, everything. Never implemented. We are working on it. It will be the next generation. Thank you very much.